Imagine an engine with no piston, no cylinder, and no moving mechanical parts. Yet it can absorb heat, release heat, and produce measurable work. This is a quantum heat engine. In a conventional heat engine, heat flows from a hot source into a working substance. Part of that energy becomes useful work, while the remaining heat is released to a colder environment. Steam engines, car engines, jet engines, and power plants all follow this fundamental principle. For example, a gas can be heated, expand and push a piston, then cool and compress back to its original state. But what happens when we shrink the engine to the quantum scale? Can a quantum system perform the same thermodynamic cycle? That is what this experiment investigates. Instead of a gas, the working medium is a superconducting Transmon qubit. Instead of a moving piston, the researchers control the spacing between its quantum energy levels. And instead of conventional hot and cold reservoirs, they use an electronically controlled quantum circuit refrigerator called a QCR. A quantum system has discrete energy states. Its total average energy depends on two things: the energy of each allowed state and how much population occupies that state. In simple terms, the total energy is found by combining the energy of every state with its population. This gives the researchers two different ways to change the energy of the quantum system. The first is by changing the energy levels themselves. The second is by changing the populations occupying those levels. The change in total energy is equal to the work exchanged plus the heat exchanged. When the energy levels change while the populations ideally remain unchanged, that energy exchange is associated with work. When the energy levels remain fixed but the populations change, that energy exchange is associated with heat. In simple terms, moving the energy levels represents work. Moving the populations between fixed levels represents heat. This is the central principle behind the quantum heat engine. The researchers use these two mechanisms to create a complete quantum version of the Otto cycle. The cycle has 4 strokes. First is adiabatic expansion. The energy levels move closer together while the populations ideally remain unchanged. The system delivers work. Next comes cooling. The energy levels remain fixed while excited state populations move downward. Energy leaves the system as heat. Then comes adiabatic compression. The energy levels move farther apart while populations ideally remain unchanged. Work is supplied to the system. Finally comes heating. The energy levels remain fixed while more population moves into higher energy states. The system absorbs heat. So the Otto cycle is levels move closer together, populations move downward, levels move farther apart, and populations move upward. If more work is extracted during expansion than is required during compression, the engine produces net work. Now let us look at the actual technology. The working medium is a superconducting Transmon qubit. Its lowest transition frequency was approximately 4.047 GHz. Its anharmonicity was approximately -279 MHz. This means its energy levels are not equally spaced, allowing controlled multi-level operation. The experiment also uses a quantum circuit refrigerator. By changing its electrical operating conditions, the QCR can heat or cool the coupled quantum circuit. This is an important feature. The researchers do not physically move the qubit between separate hot and cold reservoirs. Instead, they electronically control its thermal environment. During the off state, thermal coupling is reduced, allowing the energy level strokes to occur with less unwanted energy exchange. The entire engine cycle is controlled using precisely timed pulses. For expansion and compression, magnetic flux pulses control the Transmon frequency. Reducing the frequency performs expansion, increasing it performs compression. Heating and cooling are controlled using pulses applied to the QCR. The adiabatic strokes lasted approximately 50 nanoseconds. The thermal pulses lasted approximately 200 and 300 nanoseconds. The maximum frequency detuning was approximately -82.4 MHz. This limited frequency range is important because it restricts the engine's compression ratio and ultimately its efficiency. So the quantum engine therefore operates electronically on nanosecond timescales. But how do you measure a quantum heat engine? The researchers used single-shot readout. Each measurement provides information about the state of the transmon. For every experimental data point, approximately 10,000 single-shot measurements were performed. The readout pulse lasted approximately 2 microseconds. 4 quantum states were analyzed, including the ground state and higher excited states. The repeated measurements formed statistical clusters. A Gaussian mixture model was then used to determine how much population occupied each quantum state. Once the populations and energy levels are known, the total energy can be calculated. By tracking how these quantities change during the cycle, the researchers can determine heat and work. The researchers also estimated the effective temperature from the measured populations. They compared the experiment with simulations based on an open quantum system model called the Lindblad master equation. The experimental behavior agreed with the simulation. 3 consecutive cycles were examined. During these cycles, the effective temperature increased from roughly 200 millikelvin towards 600 millikelvin. The heating and cooling strokes did not initially balance perfectly, so the system gradually approached a saturated thermal distribution. The simulations indicated a saturation time of approximately 1 microsecond. This shows why a real quantum heat engine is not perfectly ideal. Noise and imperfect control can slightly change the state populations. So heat and work were calculated from the measured populations and changing energy levels rather than assuming an ideal cycle. Now for the most important question. Did the engine produce net work? Yes. The mean absorbed heat was approximately 4.22 micro-electronvolts. The total measured work was approximately minus 0.023 micro-electronvolts. With the sign convention used in the experiment, this negative value means that the engine delivered net work outward. The output power was approximately 0.039 electronvolts per second. Output power simply means the net work produced divided by the time required for one complete cycle. The measured efficiency was 0.0055 or approximately 0.55%. Efficiency means the useful work produced divided by the heat absorbed. The simulation gave comparable results, with approximately 0.031 electronvolts per second of output power and an efficiency of approximately 0.0045. So this was an experimental demonstration, not just a theoretical proposal. Why is the efficiency only 0.55%? The main limitation is the relatively small frequency tuning range. For an ideal Otto engine, efficiency depends on the ratio between the minimum and maximum operating frequencies. For the available frequency range, the ideal Otto efficiency was approximately 2.047%. The measured efficiency of 0.55% is therefore about 27% of this ideal value. The first measured cycles also had not fully reached steady-state operation. Simulations indicated that in steady-state operation, efficiency could approach approximately 2.2%. This shows that improving frequency tunability and thermal control could significantly improve performance. Now compare this with conventional technology. A conventional engine uses huge numbers of particles and mechanical expansion and compression. This quantum engine uses a superconducting circuit. There is no gas, no cylinder, and no piston. Expansion and compression are created by changing quantum energy level spacing. Heating and cooling are created by changing populations. Its output power is extremely small, so it is not a replacement for a conventional power plant. Its importance is fundamental science. It provides a controllable platform for studying thermodynamics when quantum physics becomes important. Future research can investigate quantum fluctuations, engineered reservoirs, and quantum coherence. Let us summarize. The working medium is a superconducting Transmon qubit with a transition frequency of approximately 4.047 GHz. Magnetic flux controls its energy level spacing. The QCR controls heating and cooling. The cycle operates with approximately 50 nanosecond adiabatic strokes, 200 and 300 nanosecond thermal pulses, and a maximum detuning of 82.4 MHz. The researchers performed approximately 10,000 measurements per data point to reconstruct quantum state populations. They measured approximately 4.22 micro-electronvolts of absorbed heat and demonstrated positive output power of approximately 0.039 electronvolts per second. The measured efficiency was 0.55%. The power is tiny and the efficiency is still low, but the fundamental achievement is significant. Scientists have experimentally operated a complete heat engine using a superconducting quantum circuit and directly measured its thermodynamic behavior. A heat engine does not need a piston. It does not need a cylinder. At the quantum scale, an engine can operate by controlling the energy levels of a quantum system and the populations occupying them. This experiment demonstrates that heating, cooling, expansion, compression, heat, and work can all be engineered and measured in a superconducting quantum device. And as quantum technology advances, experiments like this may help reveal the ultimate limits of converting energy into useful work. If you enjoyed this explanation, please like the video and subscribe to the channel. Subscribe for more science, technology, and breakthrough research explained clearly. Thank you for watching. See you in the next video.